All right, welcome back once again. This time, uh, I'm trying to provide a solutions to one of the A-level mathematics mechanics uh, problem, okay, which is requested by one of my students. Let's take a look at this. Right. Now, according to this question, a car has mass 1,250 kg. I believe that will be a typical mass for a saloon car. Now, the car is moving along a straight labor road at a constant speed of 36 meter per second and is subject to a constant resistance or magnitude 850 Newton. All right, you can see that from the diagram itself. There is a constant resistance of a magnitude 850 Newton, and then it has a mass of 1,250. Now we need to find in kilowatts the rate at which the engine of the car is working. Right. Now in my diagram, I use D to represent the driving force, not the rate at which the engine is working, but is the driving force of the engine itself. Now we know that it's moving at a constant speed. All right. Now let me show you how the mechanics would look like. Okay. Okay. Now you can see that it's moving at a constant speed. There is a driving force acting forward, and then the resistance to motion is constant. Now we need to find the rate at which the engine is working. Okay, let's take a look at what tool do we have at this point. Now, first of all, because the car is moving at a constant speed, therefore acceleration must be equal to 0 here. So we can write that down. Acceleration A in this case is 0 meter per second square. All right. Okay, so I hope that's clear. 0 per meter per second square. All right, because it's moving at a constant speed. All right, and then next would be what is the connections between the power, or sometimes they call it the rate at which the engine is working. So the rate um, of working engine is the same as, or I would say, equivalence to power of engine, right? Power engine in this case, right? Now, this power here has some relationship with the um, driving force. So if I represent the power as P here, therefore, the power is related to the driving force in such a way, right? So we say that the power is equal to the product of the driving force with its instantaneous speed at that point of time, right? And then therefore, in this case, you can say that the driving force is actually given by power divided by speed itself. Do we know the speed? For sure, we know the speed because it's moving at a constant speed of 36. So here I can actually write it down as 36 here. All right, now that will be our driving force, right? And then we know that acceleration is equal to 0. Now, next we're going to apply Newton. Newton's second law of motion in this case, right? Now, Newton's second law states that the acceleration is directly proportional to its resultant force. Now, therefore, I can represent it mathematically in this form. Now, you have to be very mindful with your F net, which is the resultant force, is not the force, unless there is only one force acting on the object itself, right? Here we have a few forces acting on the car itself, right? But we are only interested with the forces that is acting in the horizontal direction. Okay, and then the difference between the forces will give us the resultant force. So the difference will be, all right, the difference between the driving force and its resistance to motion, and then that will give us or produce the acceleration as required. Now the mass is this. Okay, we know that there is no acceleration due to moving at constant speed. Therefore, uh, that's what we have, and then we can say that the driving force is basically the same as its resistant force to motion, which is 850 Newton here, right? And then we also know that from equations number one here, driving force is given by power over 36, which is equal to 850. Therefore, the rate at which the engine is working, which is given by P, is the same as 850 by 36 here. All right. So just let me try to tabulate that, and then let's see what do we have here. Okay, so 850 by 36. So that would give us 3600 watts. But according to the questions here, they want us to leave the answer in terms of kilowatts. So therefore, we can actually write it down as 30.6 kilowatts. Right. Okay. So I hope that is clear for the first question there. I'm going to move on to the second question shortly. All right, let's take a look at the second sections to this question here. We are still referring to the same car that has a mass of 1,250 kg, but this time they changed the scenario of where the car is moving now. Now you can see that the car is moving uphill at a constant speed, again, and then subject to the same resistance as given or as provided in the previous section, which is 850 newtons here. So I'm going to write it down. The frictional force is still 850 newton, constant resistance to motion. Okay, and then the hue is inclined at that angle theta, where the sine theta is given as 0 0.1. So I'm going to write that down. Sine theta is given by 0 0.1. All right. And then now the engine is working at 63 kilowatts, because it's going uphill, so you need more power by the engine in order for the object to be able to move up the hill, right? Now we need to find the speed of the car. All right, so this is the speed that we need to discover later on. All right. Okay. Now let me show you the motions to this object first before we start to solve this. Okay, you can see that it's moving uphill. There is a constant resistance acting on the car, and then there's a driving force, and then the engine is providing 63 kilowatts of power. The mass still remains the same, which is 1250 kg. It has a weight of 12,500 newton there, moving at a constant speed, right? Okay, now we are ready. We can look at what tool can we use in this case. Okay, we are interested to find out the speed itself, right? Now, because it's moving at a constant speed, therefore we can also write down this result here. We know that it's moving at a 0 meter per second square as its acceleration. It's not accelerating at all in this case. All right. Now, the other thing we need to know of would be what are the forces acting on the car along the directions of the slope itself, right? Along the direction of the slope, right? Okay. Now, before that, I like to bring back the relationship between the driving force and the power again. So we know that the power is actually given by the driving force multiplied by the instantaneous speed at that point of time. And then here we are given the power now. So therefore, our driving force would be 63,000 because it's kilowatts divided by the speed that we need to evaluate later. Right? And then next, we need to resolve the component. Don't forget, whenever you work with a problem that involves slope, you have to resolve the component of the weight along the slope itself. So this is also theta. Uh, okay, can be proven here. Now, therefore, we're going to apply Newton's second law again. Right. Now, when we apply Newton's second law, I'm saying that I'm interested to analyze the forces acting along the slope, which is in this direction, along the slope, right? Okay. Now, considering all the forces that is acting along the slope itself, and then we know that Newton's second law tells us that the acceleration is directly proportional to its resultant force, which is given by this. I just write it down as a formality. Now, the resultant force now would be given by D, which is the driving force. There are some forces acting downward. One of them is the resistance to motion. The second component will be the weight component along the slope, which is given by, okay, now the formula would be mg sine theta in this case, and then that would produce an acceleration. Of course, we know that is because it's moving uphill at a constant speed, so therefore there is no resultant force. Okay, and then from here we know that D must be the same as F mg sine theta, and then we know that the frictional force, sorry, the same resistance force, which is given by 150, and then the mass is the mg is given by this. This is actually mg. All right, so I'll just write that down. 1 to 500. Okay, 1 to 500 by the sine. Sine is 0.1 there. Right. Therefore, my driving force in this case it will be. Let me see what do I have. 850. So 21. 21 Newton. Right. Let me check whether I got it correct. 2100. Okay, sorry. I think there is only 20 there. Okay, now there you have it. Right. So the driving force that is provided by the engine is equal to 2100. Okay, just let me verify that one more time in case I got it wrong. Okay, so 2100 Newton here. And then we know that driving force is given by 63,000 divided by the speed, which is equal to this. And then therefore, the speed, the constant speed that we wish to find out is equal to 6300, sorry, 1000 divided by here. All right. So that will be like, okay, just nice. So in this case, we have 30 meter per second. All right. So I hope that is clear. Just let me quickly check that through in case I got it right. In case I got it wrong. All right. Now after checking, yes. So the constant speed of the car as it move up the slope is given by 30 meter per second. All right. I hope that is clear for this question. I'm going to move on to the last section of this question 6. All right, let's take a look at the last sections to this question 6 here. We are still referring to the same car with a mass of 1250 kg. Now this time the car will descend the same hill with the engine of the car working at a constant rate of 20 kilowatts. The resistance is no longer constant. The initial speed of the car was 20 meter per second. All right, now you can see that from the diagram itself. 8 seconds later, the car has a speed of 24 meter per second. It has pickup speed due to the gain in gravitational potential energy and also energy provided by the engine itself, right? And the car would have been moving for a distance of 176 meter down the hill itself. Here we are restricted in our approach to solve this problem because according to the questions, they like us to use an energy method to find the total work done against the resistance during the 8 seconds there. Right. So the total work done against the resistance, which is work done against or work done by this resistive force. Right. Okay, so how do we actually use energy methods here, right? Now, let me highlight here the energy methods that you should use in the exam, the easiest to follow for A-level mathematics, right? is is the work energy principle. So I'm going to write it down here. The work by using work energy principle. All right. So work energy principle state that the work done, okay, work done is equal to the change in kinetic energy. Right. Now the work done here could be work done by many forces involved in the system itself. Right. It could be work done by the gravity. It could be work done by the engine, or it could be work done against the resistive force. And then all these resultant, you can say the resultant work done would would be the same as would actually produce a change in kinetic energy. All right. So for this, I'm going to label this as my equation number one here. Okay. Right. And then from here, I'm going to work out the change in kinetic energy. So let's look at change in kinetic energy. All right. Change in kinetic energy. All right, now let's look at what is our change in kinetic energy first. Let's look at the mechanics of this. Right, you can see that the car is moving downhill. It has an initial speed of 20, and then when it reach that distance of 176 meter, it would have gained a speed of 24 meter per second. All right. So for that, we have a change in kinetic energy of. Alright, now the formula for change in kinetic energy is the final kinetic energy minus of the initial kinetic energy. Right. So here we have mv square minus mu square here. Right. Now that would give us we can use factorization here. Okay, and then the initial speed would be 20. The final speed is 24 here. Okay, and then we try to calculate this. Let me see what do we have here. We have 625 here, and then that will be like 44, and then a 4 here. Right, that's a lots of number here. Let's try to calculate this. 44 by 4 by 625. Right, so that would actually give us 110 kilojoule in this case. All right. Now that would be the change in kinetic energy. Right. Now next we're going to work out the work done. Okay. Now the work done, the best way to work with to analyze work done would be we're going to look at which force that actually help the car to gain the speed. So you can see that the driving force is the one that um, provide energy for the car to gain that kinetic energy. So here we say that the work done by the driving force is given by d by the distance travel. Right now, this is the work done by the driving force, and then we also have work done by uh, gravity. Okay, right. We also have work done by gravity. We know that the car has typically moved. You can see that from here. The car has typically um, moved vertically through this height, right? And then this is also the data here, right? Okay. So from here, uh, you can actually obtain the vertical height, and then in order for us to calculate the gain in gravitational potential energy. So the gain in gravitational potential energy will be given by mg h here. Okay, and then after that, we have work done against, right? Now those work done against the frictional force will be given by the sign negative here. That will be Fs. Right. Okay, so I hope that is clear at this point. All right, now let's take a look at what we have from here. We have the driving force. Okay, what do we need to work out? All right, we need to work out the work done by the resistive force, which is Fs here. Right now, I might want to rewrite this as ds and then work done by resistive force. Right. Okay, now from here, this is the uh, work done, all the work done by all the forces that involve in the system itself. Right. Okay. Now let me work out each one of these components here. Now, first of all, we are still looking at the same hue here. Okay, just I just rewind the position of the car. Let me change it back again. Okay, this is where it is at this point of time. Right. Okay. Right. So I'm going to work out each one of these component now. Okay, the driving force. Right. Now we know that the car has been moving for um, 8 seconds. So 8 seconds. Rather than using the power formula. Now we do know that we have this formula here. I'm going to write down. So power equal to driving force speed itself. Okay, but we know that along the slope, the speed is not constant. So usually we don't use this formula if the speed is not constant usually. Okay, but we do have another formula that is related to power. Now we know that power is also given by um, work done. Okay, work done over time. Work done in this case, this is work done by the driving force per unit time. Okay, that's how much time that the engine is performing work in this case. So from here, I will be able to work out the work done by the engine, which is given by PT here. So this part can be written as ds. Instead of writing ds, we can actually write it down as power multiplied by time itself. So we have the power, which is 20,000. Okay, and then we have the time, which is 8 seconds. Right, now that will be the work done by the engine. And then it's going up the same slope, meaning that the sine theta must be equal to 0. Going down the same slope, so the sine theta must be equal to 0.1, which is the same as before. So here we will have, after you multiply with the height. Okay, now the height is given by, I'm going to write down here, the height is actually given by 176 sine theta, which is 17.6 meters there. Right. So from here, I'm going to take 12500 by 17.6, which is the height where the car is actually moving. So the car actually gain gravitational potential energy here. And then next we have the work done against the resistive force, which is here. By using the equation number one, work energy principle, I can relate to all the numerical value and the work done against the resistance as one equation. So here you can see that I have by 17.6 is equal to the change in kinetic energy, which is 110,000. Okay, so from here, we can try to finish up this calculation here. Just let me try this out. We have 17.6 by, all right, so here we have 16, 160, and then this part here we have 220,000, and then we have the work done against the resistive force. Okay, now therefore we can work out the work done against the resistance due to motion within that 8 second as, okay, now let me try this out. Okay, now therefore that would result to 270,000 joule, or you can write as 270 kilojoule here, right? Right, now I hope that is clear. This would be the proper way to apply the work energy principle correctly. So just remember, work done by the engine usually is positive. Work done by the gravity is also positive because it helped to um, provide the gain in kinetic energy. Right. So that's how we apply the work done principle. Work energy principle, sorry, right? So I hope that is clear and that it will be helpful in your learning. All right, until I see you again, take care, everyone.